Right, you guys able to see my PowerPoint slides? Are you able to see my PowerPoint slides?
Yes.
All right, so you're able to see my, yeah. Okay, so today we're going to start chapter 6, and we will cover chapter 6 by around 10 o'clock. So we will spend maybe 40 to 45 minutes for the first session. Then after that, we have 10 to 15 minutes breaks. Then we come back for another half of the lesson. Okay, today we're going to look at three things. One is what is a triangular element equation, and then we look some metrics, and then we solve it with the plane stress problem. So basically, what does this chapter do is that if you're using ANSYS, this chapter will be more on the discretization, or when you do meshing. This is the chapter that explain how the meshing is done. So sometimes when you run ANSYS, the ANSYS will tell you the meshing undefined or there's some error, then you can refer to chapter 6 for the explanation. Right? Okay, so today the first term of technical term, we call it plane stress. Plane stress, right? So what does plane stress mean? If you look at the diagram on the screen or on your computer or on your phone, you can see that there is a stress here, the T with the distributed load, and this one is along a plane. Along a plane. This one is along the XY plane. Yeah. So on the screen here is the textbook definition. So you can have a look now after this, right? So basically, you need to understand what is a plane stress. The word plane itself is on the plane. So you have to recall back the concept in the Cartesian plane. Yeah. So the word plane, it means 2D in a XY plane if you look at the diagram here. All right. So I draw a blue square here on the screen. It just means that that is the plane that we are referring to. And then all the force, all the stress in the Z is 0. So if you see the stress that you have on the screen here, there's no stress in Z direction. Yeah. And also the shear stress also 0. So if we talk about plane stress, it means that we only look at the blue color plane here, the stress on the blue color, right? The another one is strain. So if you study mechanical engineering, you should know the differences between stress and strain. Yeah. So these two words is very sensitive when it comes to mechanical engineering. So strain is a deformation. So you can see here on the screen is a deformation. All right. Then for this chapter, I already uploaded Appendix C in the Moodle. So make sure you go and download and have a look in Appendix C. All right. You will have all the explanation in the derivation. So I will go through very fast on the derivation. Because in coming exam, we won't test you on the derivation, but at least you understand how it works. All right, so recall what you learned in the previous module. So as you can see on the screen here, you're having a stress on the cube. In this one is a 2D dimension. So cube, you have 4 faces in 2D, and then each faces you have a stress S, Sy, right? Stress S, stress Y, and then you have a shear stress, XY, shear stress, YX. So all these substracts, sub notation already explained. So if you're not sure, you can go back to maybe in the previous slides, right? When I explained about the sub-denomination, what is XY mean, what is YX mean. Yeah? All right, so this is just a recall on what you learn about the stress and strain on a plane. When you study about a von Mises stress, this is the diagram that we start with. Right, so today we just recall what you learned, right? And then after that, we know that you can change the stress S, stress Y into the principal stress, right? So you rotate the plane, then you get stress 1, stress 2, principal stress. Okay, so for this module, you will always see matrix form. So when you see the curly bracket, means that you can expand it to 3 degree of freedom. So stress curly stress bracket equal to, so you have the x direction, y direction, and xy direction. So 2 is for stress, 1 is for shear stress. This is normal stress. The top 2 is normal stress. This is shear stress. Okay, all right. Then, like what I mentioned just now, you can change this diagram on the left to the diagram on the right here. So you change all the x, y, shear stress into shear 1, shear 2, stress 1, stress 2, and then with the angle. Delta P is a principal angle. So this chapter, stress principle 1, stress principle 2, and the angle principle is very important. Yeah. So there's a equation for that. Later I will show you which one. Yeah. So at the moment, you just take note what is important for chapter 6. Chapter 6, stress 1, stress 2, and angle of the principle, right? Of these two principles. Yeah. So this one, right? So these are the equation. So you need to put this equation somewhere, because this equation that you see on the screen is important for your coming exam. So make sure you write it somewhere. And for this exam, as long as you able to write the correct equation, you will have some marks for it. Yeah. So these are the area that you can score marks. Yeah? Don't leave your exam paper empty. Yeah? All right. And then this stress 1 equal to this equation, stress 2 equal to this equation. And then 1 is maximum, 1 is minimum. So the differences is 1 is positive, 1 is negative. So you can see the form here. Right? So this equation is important, this equation is important. Then another one is for the angle. So this is called a principal angle equation. So tangent to theta, right? Tangent to theta, which is this angle, equal to 2 stress as xy divided by stress x minus stress y. So this is the equation, right? So after that, you calculate, you change the angle into you convert, you do the arrangement of mathematics, then you get in degree here, degree. So three important equation for this morning. This one, and this one. Okay. So far, okay. Singi and Katana, are you guys all right?
Yes.
Yeah.
Yes.
Singi, all right. Okay. Good. So 3 important equation today. This one, and this one. Okay. So you have I give you 3 marks for free mark for exam already. Yeah. This one, and this one. So at least when it comes to this chapter 6 question, even though you don't know how to answer, you write these 3. You get 3 marks there. Okay, out of 25 lah. But you still need to score more marks for that, right? Okay, then the next equation is this one. So this one is the deformation that you have, but I will let you to go and read it later on from my slides. A few more slides later on will just a derivation for equation that we need to use for this morning. So this deformation. So we have a dash cube here that deformed to a solid line here. So you read through all these you already covered in the one of the either solid mechanics or static or dynamic module. So this one is just a repeat what you learn. Then you apply in this module. Okay, you read through all these slides. So you have what is the strain in X, what is strain in Y, with all these notation. Okay, and what is the gamma Yx, xy equal to this one. Yeah. So this is all the derivation, and again, you can download Appendix C in the Moodle start from today. Yeah. Go have a look. Is all the detailed derivation for the equation that we use for today for this chapter 6. Yeah. Okay, so again, we can write all the degree of freedoms in the matrix form for this chapter. Okay, then one important cases for chapter 6 is that when you look at plane, all the parameter in Z is 0, yeah? Stress 0, shear stress 0, and so on. And just to recap, what you learned from chapter 3, chapter 4, chapter 5, we can always link the unknown together with the metric. So in this case, previously you learned about F equal to KD. Now today we have the converter here with the stress equal to matrix D times the strain. Matrix shear stress equal to our converter matrix here D times the strain. So you know that this is the matrix that we're going to use, and there is a format for D. So as you can see here on the screen. So I don't expect you to memorize this one, but at least you've seen this one before. And you write somewhere in your notes because this equation also important for chapter 6. So chapter 6, beside the 3 equations that I showed you just now, another one is you need to find stress and strain for chapter 6, right? So every time you see stress, this symbol and this symbol, you need to take note. It's important. And the detail of the matrix, this complex matrix here, I don't expect you to memorize, but at least you copy and you put somewhere in your notes. So this is important. Right? The format is standard already. You just need to substitute the number inside the matrix, and then careful on the calculation, especially when you use a calculator. Be careful. All right. So stress equal to D times the strain. So then you use this converter to convert between these two. All right. This D, we call it stress or strain matrix or consecutive matrix or D. Right. Right. So the fourth equation for today, stress equal to D strain. So this is the fourth one. All right. Then the rest is just repeat what you learned. Okay. So as you can see here, stress equal to D strain. So you can replace the stress with the 3 degree of freedom here. Strain is another 3 degree of freedom here. All right. So you just do the converter later. We will give you one tutorial question and then to see how we apply all the equation that we learned today. Okay. Another one is strain. So just now what we look at is stress, plane stress. Another one is strain, right? Plane strain. So given by this equation. So plane strain also have plane strain. What is different is the D. Is a D matrix here. The converter matrix is a little bit different. So there are 2 format of D matrix. One is for stress, this one. If you want to do plane strain, you need to use this converter, this D matrix, which is given by this form. Okay, so make sure you know how to differentiate between 2. The longer one, when you get a longer one, it means it's the plane strain. The shorter one means you use it for plane stress. Okay, this is how you differentiate it. Okay. Then just recall this symbol like V, Greek V. This is a Poisson ratio. Yeah. So yeah. If you cannot recall what is Poisson ratio, you can Google, right? Poisson ratio. It's important if you study material, Poisson ratio. And then you will see all these complex equation, right? Okay, so there are derivation steps. So I will just go very fast on this. So as you can see on the screen here, you have a thin plate in a tension. Tension means you pull on both ends. And then the middle one is a discretized plane where you will see it in the ANSYS software. Okay, so you change the top diagram into a bottom diagram. So bottom diagram, you see a loss of triangular. So in this module, we will use triangular elements analysis. So we will change the, in this case, we will change the rectangular shape object into a loss of triangular elements, like you see here. Okay, so when you break into a loss of triangular, we start with a small triangular like you see on the screen here. So this, how you define a triangular, we need 3 points. So we start with the I, J, and then M. So as you can see here, the direction that we use to define the point is anti-clockwise. Okay, it's anti-clockwise direction. I, J, and M. Okay, I, J, and M. N is a number of element, a number of triangular. So from this point onwards, be careful on the direction that we use for triangular element. So we start with the bottom, go to the right, and then go up. I, J, M. Then later on, the equation that you see, the sub notation. If you see I, it means refer to the first point. If you see J, it means that you refer to the second point. If you see M in the equation, it means the third point. Okay, all right. Clear, Katana and Singi? Katana, any question?
This is done manually, is it?
Yes, there is an equation for it to calculate. And yeah, for a few more slides later on, you will see there's a step for derivation. Means you will see that how we calculate stress and strain from this little triangular. Then we integrate into a very big picture. What is happening in this plate here. So later we will start with very small element. Then after we get one element, then we integrate. Let's say this big split here, we break into 1, 2, 3, 4, 5, 6, 7, 8, 16 triangular. So we will start with one small rectangular. Then after that, we times 16. We get, not times, but we integrate. Then we get the total stress that we have. Clear, Singi and Katana?
Yes.
Okay, let me see slide here. Okay, lights here. All right, good. Okay, again, for this chapter, you'll see a lot of steps in derivation. However, we'll keep repeating the same 7 steps for this module. Either it's from chapter 2 alone, chapter 2, 3, 4, 5, 6. We keep repeating the 7 steps of derivation for our element stiffness. So we keep repeating the same thing. So step 1, you select element type. Step 2, you create the displacement. You select the displacement function. Means the first one you count what is the element you have. Like for this case, you have IJM, 3 node, and then 1 element. This is the first step. Second one, after you have the function or equation, F equal to KD previously. In this case, we look for stress and strain. So you use the stress times the D function converter times the strain. Then you solve for the displacement first. After you solve displacement, you solve for all the forces that you need. So first, element type. Second, displacement function. Third, stress and strain relationship. This is we keep repeating the same thing. And the fourth one is the stiffness matrix. We go for elements, stiffness matrix, then we combine into a global matrix. Right. Step 3, 4 is keep repeating like what we learned from chapter 4 and chapter 5. And then we assembly. And then after assembly, we want to solve the question, the equation. We apply the boundary condition. So if it cannot move, the a row and column, you close it, and then you will simplify your matrix. Then number 6, you solve for individual nodes, displacement. Then the rest is either you solve for the force and stress. Okay. If you look textbook, step 1 to step 7, it will be around 5 to 6 pages. So I already simplify into one slide here. So as long as you can remember step 1 do what, step 2 do what, until step 7, then you are fine for this chapter. Okay. All right. let's look at this example and then see what we can do. So step 1, what you do is what you do in ANSYS, call it mesh, but for this chapter we call it discretization. Right? Discretization means we break into a small pieces of element. Okay, in ANSYS we call it meshing process. So yeah, step 1 is just break into a small element that I highlight in the screen here, and then later we'll use this diagram for our derivation. So you can look, you can go very fast for step 1 to step 7. Then we look at the application. All right, important is how to apply. All right, so as you can see here, we have 3 point IJM, and again remind yourself that we are having an anti-clockwise direction when we label the 3 point. So I, J, and M. So each point will have the displacement. So you have the displacement in X direction, which is U, the displacement in Y direction is V, same with other 2 points. Then we are using, yes.
Do they have to be triangular elements, or can use different shapes?
In this chapter, you need 3 points. It doesn't, as long as you have 3 points, then the shape of the rectangular is not an issue. As long as you have 3 points, then you combine these 3 points together. Okay. Understand? Yeah. So we start with 3 points first. Then of course later you can add 4 point, 5 point, 6 point. So the simplest element is 3 point. Okay. So yeah, so this is a Cartesian coordinate. You have x sub I, yi means refer to the first point, and then same with the other 2 points, right? So if you see xj means the j point, xm, ym means is referred to the m point, the third point, right? On the diagram or in the analysis. Okay, we move to the equation. So don't get scared with the direction with the equation you see on the screen here. Basically, you're just repeating the same concept. So D means displacement. So you have 3 points. So displacement in I, displacement in J, displacement is in M. Okay. And then you can expand the displacement when you write your matrix. Your displacement will have, each point have two direction, X and Y. So for example, the point 1, you have UI, VI. Second point, you have UJ, VJ. Third point, you have UM, VM. So you just repeat what you learned in chapter 3 and chapter 4. Right, so this is a displacement matrix that you learned previously. We just changed the subnode here. In this case, because we look at triangular, we are using IJM. So you just substitute the previous 1, 2, 3 to IJM, right? Okay, the next step 2, we look at the displacement function. We will use linear displacement. So linear displacement means a linear equation. So you can look at the screen here. So I will not go deep lah. So you can read this one after this. You can read my slides later on. So all these are the linear equation. I'll go very fast. All right. So another symbol, a new symbol that you see today, will be the general displacement function, which is the pi here, right? The pi symbol. So pi symbol actually is combined the previous linear equation that you see on the screen here. So every time you see this pi function, it means refer to chapter 6. This symbol only appeared in chapter 6 for plane stress and plane strain. Right, you compare these two and you have two equations. every time we have equation, you know that you can convert equation into matrix form. Okay, so I'll go fast for the previous slides, for the next slides. So you can convert all this equation into matrix form. All right. The rest you can read from my slides here. So these slides on the right hand side, the information on the right hand side, basically I just expand it in according to each point location based on the blue color equation that you see on the screen here. Okay, all right. So what is important on this slide is this general equation that I highlight with my mouse movement. This one, yeah. This is the, we call it just now, we call it the general displacement function. Okay, you read through my slides. So basically, again, when you see equation, you have 6 equation here. You can combine these 6 equation into the matrix form like we see here. Right? We just summarize these 6 equation into a very simple matrix here. You can see U equal to something matrix equal to the constant value A1, A2, A3. All right, so we could just convert these 6 equations into a matrix form. Okay, so yeah, so this one you can do it with the calculator that I show you, the online calculator. How you do the inverse, you just key in the number, press the inverse, then you use the value, import here and there, and then you'll get the answer. So on these slides, again, you need to go back to the concept of cofactor. What is cofactor? This mathematical model. However, with the tools that introduce you with the online matrix calculator, it should not be a problem for you already, right? So the equation is there. So you just need to apply, substitute the value there, and then you key it into the website, and then you press the convert into inverse, then you get the value. What is important here is the determinant in the matrix here, 2a. 2a equal to this equation is important equation here. 2a, a is the area of this triangular, yeah. So just put a note on the screen here. So a is the triangular area. Okay, so again, you'll see a lot of equation for the alpha I, alpha j, alpha m, bi, bj, bm, gamma 1, gamma j, gamma m. So all these, we have a 6 equation here. Again, you don't need to memorize all these. These are the standard equation that you can refer to my slides anytime in the exam, right? So you can write it somewhere in your answer also. So this one will give you some marks also, right? Maybe 1 to 2 marks, just to copy out these 6 equation, then you get marks for it, right? So this equation and this 9 equation, right? So important later, you'll see in our example, we'll use alpha I, alpha z, alpha m, and then we substitute all the value here. So for example, how you calculate alpha I? You take xj. What is xj? Is location of this one times ym. What is ym? Is the location of your m node ym minus yj. So again, the sub j means you refer to the j point. What is the location of this point? Xm, you refer to x location, m node, and so on. Repeat the same for the other 9 equations here. Okay, so this slide is important for this 9 equation here. Okay, just plug and play, plug and calculate. And this is another equation that we will use, all right? Right, later we go through this one. Yeah. Okay, so again, lots of equation on this screen. Don't worry, you just read through the PowerPoint slides. And yeah, you just read through. So this is basically the derivation steps to get the displacement, right? To get the displacement, right? A lot of equation, don't worry. You just read through, yeah. Just read through, huh? So we just simplify with all the and so on. So don't worry about it. Just read through again. Okay. All right. So another concept here, you can see that the phi or the pi curly integration pi equal to nd. So n here is the another matrix that you will see in chapter 6. All right. So there's a name for n actually is the shape form, the shape function. Yeah? So each n we have all the equation here lah. So again, don't worry if you need to use ni, you just refer to the slides and then you copy the equation out. Huh? Lots of equation for today. Okay. Now what you see on the screen here is the another two important equation that every time you want to find the gamma here, the general displacement equation. So if you every time you want to find the displacement on the plane, then you use the equation that you see on the screen here. Right. If you want to find the general x displacement, general x displacement, so you use this matrix. Okay, you use this matrix. All right. So again, we are chapter 6. We look at plane scenario. Plane scenario means all the stress and strain on the plane itself. Okay. So these are the deformation that can happen in the cantilever beam. We will use a strategy called constant strain triangular, or in short, CST. So CST is a strategy we use to solve finite element analysis on a stress element. So you can either move to the left or right, move up and down, rotate to a certain angle. So these are the movement or deformation that can happen, right, on the element. So on these slides, you can see that in a finite element or in the ANSYS software, if you have a distributed load and then you have all the meshing happening, so you can see that after analysis, you can see that the ANSYS will show you, the software will show you the deformation, the result after you applying the stress. So this is what is happening in the calculation, right? So this is basically just a schematic diagram and what happened. All right, so again, you go through all the equation. So this one is all the equation, right? So you read through all the. Just now we look at the stress. This slide is more on the strain. Yeah, strain. So you read through. We repeat the same strategy. You'll see the M and stress equation again. You read through all the slides. Okay, read through all these equation. Don't worry about it. Just read through. All right. Then you arrive at one important equation, with the strain equal to 1 over 2a, the matrix, and the displacement. Okay. Yeah. So if you see beta, means you're looking at the stress and strain, the strain here. Right. So this is a complete set lah. The complete set if you want to find the strain. Okay. Okay, so this is the set of equation when you want to calculate the strain. All right. So again, that what is Bi, gamma I, this one is standard already. There's an equation for it. Yeah? And what is B matrix here, also standard already. You have these three set of equation. You just substitute the value inside there, right? Now what is Bi? Bi, there is an equation for that. B value just now, there's a slide for it. Let me find for you. There are too many equations already. This one, this 9 equation, right? 9 equation that we always use back this 9 equation. Alpha, beta, gamma, right? Okay, so you read through lah, all these slides in my PowerPoint slides. Okay. So again, for strain we use strain equal to B matrix times D. Yeah, for strain we use strain equal to BD. For stress just now, stress is, we use this one. Let me find for you. Stress. Stress is this one equation for that. Never mind, later we'll come back to the equation again. Okay, we continue. So we have one set of equation for stress, strain equal to BD. Yeah? Yeah, there's a converter. There's a conversion between the stress and strain. So just now we see the stress, the strain equation. We did this one. Okay. Let me show you. Yeah. Sorry, there's lots of equation today. Okay, so just now you calculate the strain with this matrix, strain equal to BD, B with all the equation you see on the screen here. You calculate. So this is the a simple form, strain equal to BD, and then if you ask to find the stress, you use this equation. You do the converter also. So you calculate stress, because the relationship between stress and strain is stress equal to D strain. So you substitute what you learned just now. You will get stress equal to dB, the capital D, times the matrix B times the D. So you get this equation. So what is you need to memorize is this one. Strain, you use this equation. Stress, you use this equation. Okay, stress is this equation. The rest you can refer to slides. Don't worry. All these are standard form already. Okay, we continue with the step number 4, which is a little bit more complex. So you read through the slides. So with all the omega shape and all this. So what is important for here is that when we look at potential energy, we will look at four type of energy there. Potential energy, one is the strain energy, the first one, U, which is we will look at the, in this chapter, U, and there's an equation for it. And then we look at the body forces, we look at the concentration load, and then there is a surface traction. So if your system, the system will always start with the its original strain energy. Then if you have a gravitational force, then you have a body forces. Then if you have a concentration load, then you calculate the third term. If you have a distributed load, then you add in the fourth one. So this is the total potential energy inside the element. So this equation is also used inside the ANSYS to calculate the potential energy or the energy, the strain energy, the stress energy in the calculation. So this is the general equation that we use. Right, you read through with all the complex triple integration formula. I label as a red color because it's quite complex, but anyway, you can just always refer to the PowerPoint slides. Yeah. This slide, what is important is that you know that there is an equation to calculate each one of the, and then you know where to find all these equations. So you have four set of four set of equation: red color, green color, blue color, and yellow color. So these are the equation that you use every time the question asks you to solve strain energy. If the question asks you to solve strain energy, you refer to this red color equation. If the question asks you to find body forces, you use the green color equation. If the question asks you to find concentration load, you use this maybe a little bit purple color equation. And then if the question asks you to find the potential energy of distributed load, then you use the yellow color equation. Okay. All right, so then you combine, you summarize, you read through my slides. All these are mathematics steps, so I don't want to confuse you. You read through, there's steps for that. At the end, you'll arrive at one simple equation with these slides. You always use K. The important in this chapter 6 is the element stiffness matrix, which is K equal to T, A, B, curly matrix, T, T transpose matrix, D, B. So all these have its own equation. So don't worry. You just if you want to, if you need to find the D matrix, you refer to the slides that help you to find D matrix. If you want to find the B matrix, again refer to the slides. This equation for it. Transpose, this one I cannot help you. Transpose is you just switch the location inside the numbers. So again, if you forget what is transpose, you can use the online matrix tools to help you. You can convert it for you. A is the area of the element. T is the thickness. Right? T is the thickness of the material. Okay, so beside the four equation, important one. So the one that you see on the screen here is another important equation for chapter 6. K equal to TABDB. So this is the equation that we will always use for chapter 6 question. The rest you read from my slides. Okay, so each one of it have its own equation. You just read through. So K matrix, you have 3 times 3 matrix. So each one have its own equation. For example, KII, it means you use this one. TABI transpose DBI. So if II, it means the first one is I, the second one is I. So for example, if you look at KIJ, means I means the first row, first row, second column. So IJ. So IJ means the first B here, you use the BI, second one you use BJ. The third one, for example, KIM. So the B, the first B that you use is BI. The second B, you use the MB. So BI, BJ, BM, there's an equation for that. The 9 equation that I showed you just now. Right, you just calculate and then you substitute inside the K matrix. Then you repeat F equal to KD, you solve. This is, you should be familiar already with this form, F equal to KD. So you have all the force on the left hand side, the matrix in the middle, the displacement at the right hand side. Then you recall the equation for potential energy. Again, this one you read and use my slides for your answer. So recall the 4 type of energy you have. And recall the K matrix you have. So this is the summary of the potential energy, the equation, the important equation. U with the strain energy equal to 1 over 2. D matrix T, T means transpose, K and times the D. So you'll get the strain energy. If you want to find strain energy, you use this equation. Number 5, you just assembly all the K together. You get the capital F, capital K, and D. So just now, from step 1 to step 4, you have all the small f there. Small f. When you come to step number 5, once you have the all the element K, you combine all element K. The F equal to KD equation become the capital F, capital K equation. All right. Step 5 to step 6 is what you learn from chapter 3, chapter 4, and chapter 5. So these are all the equations that you use. So this slide is important when you want to calculate. So these are all the standard metrics that you use. So if you see D prime, you use this equation. If you see the F prime, you use this equation. If you want to calculate the element K, then you use this equation. Now, if you see the prime, what does it mean? Prime means that you need to convert the element axis into global axis, like what you see here. So every time you see the D prime, F prime means you need to do conversion from the element axis itself, like what you see on the screen here. You have two axes, two types of axes. One is the Y prime, X prime, which is on the element itself. Another one is the global matrix, the global axis, which is the Y and X. Okay, so just take it in this way. Right? Every time you see a prime means you need to convert the element dimension into global dimension. Then the rest of the matrix, here you have a 6 times 6 matrix. It's quite big, but it's a standard already. So you just need to copy from the PowerPoint slides. Okay, so the side note here, I put UI, VI, UJ, VJ, UM, VM. This is just a coordinate for all the numbers here. Same with the top. Here. You can write it top or you can write at the side here. Okay. So means first two column is the point number 1. Middle 2 column, point number 2. Model, the last 2 column here is the two column here is the third point, like what we practiced previously. And then you solve for displacement, solve for the forces. Okay, I think we stop here. Then later we will look at this example. Okay, stop the recording. We will have